anybody's missing. So looking into into our first model here, our first model, folks, is the decision tree. And there are a category of different models that are different types of trees. So you're going to see trees more than just this one lesson. And in general, our decision trees are used for classification, supervised classification. In fact, all of our classification will be supervised, just like our regressions. It is also technically possible to use a decision tree as part of a regression. That's out of scope for what we're doing here, but it's possible. So starting at the top, we can't lose sight of this fact that classification is a supervised machine learning process. And so all of the data sets we're going to be using have some labeled data. So supervised double equals labeled data, double equals answers. And we've talked about modeling in general, that all of our classification models are trying to produce a decision rule and produce a decision boundary, right? So depending on the different type of classification model we're using, the mathematical methods change from decision trees to k-nearest neighbors to random forest to logistic regression. The math is different, but the main goal is identical with all of our classification tools. All of these different classification models are trying to produce a decision rule that we can use to classify future data, right? So what makes decision trees different? Why do we start with decision trees, and what's the big idea? Well, a decision tree is actually fairly simple underneath the hood. It's essentially like playing 20 questions, and we're not limited to just 20, and we don't have to go up to 20 depending on the needs of our data. But with each question, we have a binary, a yes or a no, with each decision point on a decision tree. And again, each decision point is helping us produce that decision boundary. Okay, so if we're comparing to 20 questions, the number 20 is what's called the depth of our tree. That's how many decision points there are in that tree. And we have to be very careful around this idea of how deep the tree is, because if we don't purposefully set the depth of that tree to a specific, there's an argument that goes into the decision tree instantiation. When we make that model, our decision trees will become, by their very nature, overfitting machines. So if we don't dial in the number of questions, imagine that the code will do infinite questions, or not necessarily infinite, but enough to where it will learn the training data perfectly, which is the textbook definition of overfitting. When your model knows your training data so well, but it's like it's taken a certain test, but it has less of an ability to generalize to different data. So overfitting is a thing that can happen with trees if you leave out how deep your tree is going to go, okay? Or if you purposefully or accidentally have a very high number or a very high depth to the tree, they become overfitting machines. Very easy to overfit. Okay. So we will see overfitting in some of my example code once we get there. So I'm going to start with a high level, and then I'll get into some example code. And I have two different data sets I want to show you. One, it matches the curriculum one-to-one, and another data set is the tips data set to show us a different, same tool, different target variable, right? So decision trees are, what we end up doing with our decision tree is we produce a sequence of rules. And that sequence of rules, again, a set of decision boundaries, right? We can use those rules to classify two or more classes. So decision trees are just fine and dandy for binary classification. Also, they can handle multi-class classification in case we have 3 outcomes or 5 outcomes or 10 or more, dozens, right? And so the language here is each decision point, this idea of a node on the tree, each split point represents one single variable at a time, and a split point around that. I'll give you an example in the diagram below. The leaf nodes of the tree contain our output variable, and the leaves are the very end nodes, are the output, right? And our predictions are made by walking across the split of the tree. This is really like playing 20 questions. So when we take a peek at the Titanic decision tree, based on the when we look at the most important feature, the gender in there, then we can survive. We have a yes or no question around in the data. What's a binary? So generally, our on a decision tree on the diagrams, our yeses go to the left and our no's go to the right. Right. So we see, even though this image is green, usually green means good, but those folks perished, right? So looking beyond that, the next most important decision point, and I'll talk about how the just a little bit about how the decision tree ranks these decision points. The next decision point is, okay, if the gender is male, then we ask the next question. The next most important question is the age greater than 9.5, right? So then we're looking at, okay, there's a prediction of death. And if there's not, then there's another decision point, right? So looking at this example, we have how many bold lines, how many split points do we have? 1, 2, and 3. So the depth of this tree is 3. It's making 3 different decision points, and it's trying to classify everything that it can based on those decision points. We can completely control the depth of our trees, but with a decision tree, the very first question is always going to be the most impactful in terms of bang for your buck, right? Let me say that without a turn of phrase. It will be the most impactful on splicing up the data into a yes or a no. The second decision point on a decision tree is the next most important. And I'm going to gloss over, I'm totally going to own this. I'm going to gloss over the mathematics that makes this possible. But think in terms of the Titanic data set, the gender decision point was pretty evident, right? It leaps off of the screen at you in the data exploration, right? Now, what's going on is the decision tree engine underneath the hood is trying to compare how much data, how much information do we get from each decision point, and it puts all of the decision points in a ranking and puts the most important at the top, right? And there are 2 methods that the decision tree classifier can use. It either uses a Gini coefficient, something called a Gini, G-I-N-I, a Gini coefficient, or entropy. Doesn't really matter which one you use in practice, actually, but they're all different ways. They're both different ways of measuring how important is that decision in order to rank them. Okay. So I'm not going to give you all a doctoral thesis on Gini coefficients or entropy, but the thing to know is that the decision tree at each decision point is trying to measure how much information each new decision point gives us. So when we look at the Titanic data set, no matter how you slice or dice that Titanic data set, this first decision point is always going to be the most important, just based on the numbers, right? Just based on the numbers. And every decision tree is going to work in the same way, okay? Regardless of the features, it will rank the features of importance and make the most important decision point first, and then the second most important decision point, and then the third. And so that kind of hints at the fact that the deeper our tree goes, the more we're splitting hairs and getting less and less value for each split point. Does that make sense? Cool. A lot of pros for decision trees. They're very easy to understand. They're very, very simple to visualize. I'll give you an example of that. We could just produce a PDF or a JPEG or something that is a chart that looks like this, little bit different formatting. But we can explain this to non-practitioners. You can explain this to the C-suite, right? You can explain a decision tree in court on the stand, right? Which is important. It's pretty critical. And it's fairly simple to explain the output. Something that when I'm feeling lazy is definitely a pro. A decision tree does not require quite as much data preparation, and one of the things that we can skip for right now with decision trees is scaling our continuous variables, because decision trees don't care about scaled data. It won't make a difference to them. The mathematical reason why is because they're drawing a decision tree is drawing lines perpendicular to either its x or its y-axis or whatever axes we've got. But we will get into more data preparation in regression, so we can properly scale things. We've been hinting at this already, but there's enough going on in classification right now. We just want to focus on what it takes to get something out the door. Another pro with a decision tree, we don't need to encode our target variable. And that's kind of nice. And generally trees have good performance, generally pretty good performance. Here are the downsides. A decision tree can create complex trees. That's how deep your tree is, right? That do not generalize well. So by their very nature, if you let a decision tree go all the way, as deep as it wants to go, we will probably have as many split points as we have observations if we don't manage that ourselves, right? And that means that we have an overfitting machine, a machine that gets really good at training data but doesn't perform as well as on validate or test. So we'll talk about in the code demo, we'll talk about some ways to handle that. Yeah, overfitting is the big one. Okay. Let's see. Again, you've seen this diagram before. The decision tree itself on top, 1, 2. This decision tree has 2 decision points. The tree depth is 2. The very first question, is the petal length less than or equal to 2.45 centimeters? This one right here that breaks off all of the setosis. This gives us a lot of information. The yes means we are in setosa territory. The no means it's either versicolor or virginic. And we know that the iris data set only has 3 outcomes. So this first decision point is producing quite a bit. It's getting all the setosis. Second decision point, it's going to do a reasonably good job of getting all the versicolor and the virginica. So we can visualize the decision tree like the above diagram. And if you wanted to chart this stuff out, we could plot out the petal length and petal width, and with some we could, if we use the hue argument in Seaborn, we could separate the yellow from the blue from the brown, and we would be able to eyeball this, right? But rather than eyeballing, the decision tree algorithm is going to try and maximize its ability to be right. How we doing? How we doing, folks? How's the pace? Too slow? Just right? Too fast? All right, cool. Cool. So again, we're playing 20 questions, and that question may be one or 2 questions if that gets us to where we need to be. And we can visualize our outcomes. All right. I am at the part of the episode where I want to show off some code. Are y'all in a place where you want to see some code? All right, cool. So conceptually, decision trees are really nice. They're kind of like a flow chart for understanding the data. And what I'm going to do is use the first example I'm going to give us is a binary classification with a decision tree. I'm going off-road a little bit. I'm going off-road from the curriculum. All of the code examples are the same, but the data set is different, okay? So I'm gonna do all of my imports here. Let me start this over. And we're gonna make a decision tree around the tips data set. And that tips data set is information from a restaurant. And I'm going to do all my imports. Some new imports we're going to be doing here. And this is because we are, let's see, import the warnings, NumPy, pandas, PyDataset, because I'm going to get my data from PyDataset. And then these lines from sklearn, model selection, import train test split, that's super important, from sklearn.tree. So sklearn has a library called tree, and there are different kinds of trees. We are specifically importing the decision tree classifier. This is really a great hello world kind of first classifier is the decision tree because it's easy to visualize. So we're going to import the decision tree classifier. We're also importing something called export graphviz, and graphviz will allow us to produce a diagram of what our tree is doing, and then all the decision points. So that you can take that printout of the diagram of the tree and use that to explain your work, right? If it's on the stand, or if you need to explain things to the C-suite, right? We're also going to import the classification report and the confusion matrix, and then Seaborn and Matplotlib for good measure. GraphViz itself is another library. If y'all want to go through this, you might have GraphViz installed already with Anaconda. I'm guessing like a 70% chance you might have to install it with pip on your own. Okay, so I've got all my imports in. Then I'm going to define my generic splitting function. This is one I like to use because it gives me a nice train validate test split. And if I send in a column to stratify by, it stratifies it by that column. If I don't, it doesn't, right? And I get the 3 data frames back, train, validate, and test. So with this specific data set, the tips data set, I think you all may have seen this one before. We have total bill, tip, gender of the person who's paying the bill at that restaurant, whether or not that's a smoking table or if anybody's smoking at that table, the day, which is Thursday, Friday, Saturday, or Sunday, the time is lunch or dinner, and then size is the table size. So what we're going to do here is we're going to use all of the features except for smoking status as our input features. And let's say the owner of this restaurant came to us and they say, hey, you do magic with math, right? Tell us if we can guess if somebody's a smoker or not, right? And I'm picking this target variable out of a hat. It's probably a little bit more believable in the scenario. Hey, based on my customers, can I predict if at some point in their meal they're going to want to smoke, right? With a decision tree, we could focus on the gender, the smoking status, the day, the time, the size of the table, anything that's categorical, right? So here's something that's kind of nice. We don't need to scale our continuous input variables because we're working with a tree. That's just a nice benefit of working with trees. We'll talk about scaling later. And instead of strings for dinner or lunch or the string female or male, what I'm going to do is turn those into a binary. So I'm going to make a column called is female, another column for is diner. And then this day column here has 4 possible outcomes, Thursday through Sunday. So what I'm going to do with that day column is I'm going to do get dummies on the day. Then that gives me my dummy data frame. And then I'm going to concat the dummy data frame with the original data frame and drop all the unnecessary columns. And we'll take a look at the processed and prepped data. Okay. So now we have the following variables, the following columns. We have total bill is a continuous number, tip is a continuous number. Smoker, notice I didn't turn the smoker into a binary. I could have, but I don't have to. And this is another little bonus of tree-based tools is we don't have to encode the discrete target variable. So the smoker, there's only 2 options in this data set. There's not like sometimes, right? Or not like only a cigar on somebody's birthday, right? It's yes or no in this data set. And then all of these other columns are either numbers or they've been converted into a Boolean, okay? So looking at the dummy variables here, I have day sat, day sun, day thur, and Sunday is one of the options. So if we have 0, 0, 0 on these 3 days, it means that we're talking about a Sunday, okay? I'm sorry, a Friday. Okay, so not a lot of heavy data prep, not really super heavy data prep. What I'm doing is turning anything that's a string into anything that's a binary string in the data set, turning that into a number instead of just a string as a categorical. If I have a categorical variable that has more than 2 outcomes or more than 2 possibilities, then I'm going to do the get dummies. And you can do get dummies on as many columns as you need to get the job done, right? In this specific data set, the only categorical value that has a whole bunch of options is the day, because there's 4 options. And that's why I'm doing the get dummies on that one. Okay. So our data is squeaky clean, and it's clean enough for a decision tree, which is great. And again, the getting to a rapid model is one of the benefits of a decision tree, because we're not scaling the numbers, and even if we did scale them, we're comparing dollars to dollars here, right? So it's not that big of a deal. So we're going to split our data. What are we doing with validate and test? We are not going to touch those for right now. At the end of once we've built a model on train and we've figured out if the model is even valuable enough to move forward with or not, then we'll use the model that we trained on train data, evaluate how it performs on validate, which is out of sample, right? That's unseen data from the model. And then if we want to build multiple models, we can use multiple models against the validate data set, looking for the right model, or the best performing one, and then the best performing one we used on the test data set. Okay. In the lesson here, I'm going to skip that last step. And so I'm taking my data frame and stratifying by my target variable, if I can. And then I've got a shuffled up split data set. So far, so good.
So we are stratifying on smoker because that's the one that we're focusing on, correct?
Mm-hmm. Yeah, I don't want that, because smoker is the thing we're trying to predict. What I'm doing here is I'm saying, hey, split functions. And remember, my split function is kind of generic, but underneath the hood, it's calling the sklearn train test split. And when I set a stratify variable, what we're doing is making sure that we don't accidentally, by random, have a clustering or a clumping of the target variable in the train that doesn't show up in validate, that doesn't show up in the test. Right? We're explicitly saying here, hey, sklearn, make sure that you get you do your best to get an even distribution of the smoking status between train, validate, and test. So
thank you for that reminder.
Yeah, absolutely. I'm glad you asked about that, Amanda. Yeah, that is I don't want to say 100% of the time, but generally, if that's the thing we're trying to predict, we don't want to end up with because the splits are random, right? But we can constrain that randomness to say, hey, make sure the 3 buckets, the train, the validate, and the test, that they have roughly an equal amount of smoking status, if we can. Because it really comes down to stratifying means we're making representative data sets between train, validate, and test, right? If we don't do that, we might end up with non-representative data sets just because of randomness. Yeah. Cool. Good question. So we've done our data prep, and now here's one more little kick of data preparation. And what we're going to do is take the train data and split it up into the x's and our x and our y. Now, it's a custom for our target to be a y variable, right? We've seen this in algebra when we have y equals f of x, right? So we're looking at some output. So the thing that we're trying to predict is y. And when we look at the x, that x could be one column, it could be two columns, it could be 100 columns, depending on your data. And what we're doing here is I'm saying, let's take the train data set, which is everything you see above, and use everything as a feature except for the target variable, right? And then we're going to specifically say that the y train is, remember, labeled data, right? Or labeled data means supervised algorithm, right? So we're putting aside the correct answers for the y for later, so we can evaluate if the model's any good. Then we do the same game all over again on the validate data set and on the test data set. Depending on your split function, I've seen some folks build split functions that take in one data frame and give you back these six different data frames, or I'm sorry, these 3 data frames and 3 series, because the y is a series here because it's just one column. So you can have this as part of your prep or separately, whatever works for you. Okay. So I want to check in and see how we're doing on the prep side of things. Any questions on the prep side of things? The splitting, the stratification, why we're naming things X, why we're naming things Y, why we're dropping the target for our X variables.
I want to make sure that I understood a bit further up the concatenation. So you had changed everything to Booleans. And whenever you made the dummies,
Yeah.
I see, oh man, I think I just have to go back to my notes because I know I wrote something, so I remembered with the dummies. But I see that you put it on there, but then immediately dropped it.
Oh, perfect. Let's get it. Let's zero in on this a little bit. So this dummy data frame is going to look like the following. So I'm gonna acquire my data again. I'm gonna prep it again, and see how I've split the dummy data frame. So this dummy data frame is just these 3 columns here. So if we had seven days, we would have, because I'm dropping the first, we would have 6 different columns here.
Okay, so doing the dummy underscore df, that's actually turning it into zeros and ones, or encoding it.
It's turning the day column into a data frame containing.
Okay. Yeah, I see that now. And then up above, we turned that one into Booleans with the equals, and we dropped on the next one because we no longer needed the unencoding.
Correct. Because the only column that the decision tree can survive, can actually do any work on without encoding is the target, which in this case is the smoking status. I could have turned that into a Boolean too, but I'm trying to just show us that we don't need to encode the target with a tree.
And that's where I was confused. I was like, I thought you said that we didn't have to encode, and yet we're encoding, but it's to get rid of the noise.
We need to encode our features. Our features are the things we're using to predict. The target is the thing we're trying to predict. And strictly speaking, a decision tree doesn't need our target to be encoded. Okay.
Just to add, another question. So would it be better to use ones and zeros for is female, or trues, or bools, or does it matter? Is it preference?
Doesn't matter.
Okay, perfect.
Doesn't matter. Zeros and ones are pretty quick computationally. Strictly speaking, a Boolean array is a little faster. But I mean, we're splitting hairs at a processor level, and I mean, we don't actually need to worry about that too much. So I'm dropping the columns that had plain text in them because I've turned the time is either dinner or dinner or lunch. So this is either going to be true or false. In this particular data set, the gender observation is a binary. So we're using that binary here. And then we're turning the days of Thursday, Friday, Saturday, Sunday. We're not turning those into numbers per se, because we don't want to say that Sunday is higher than Saturday, right? It's higher than Friday. So what we're doing is we're converting those into, this is a type of encoding called a one-hot encoding, the get dummies. One hot means that only one of the options on each row is 1. Everything else is 0. That's where the one hot means. And think of it as a little switch. So this first observation, is it Sunday? Is it Saturday? No. Is it Sunday? Yes. Is it Thursday? No. When we look at the last observation here, is it Saturday? No. Is it Sunday? No. Is it Thursday? Yes, it is. And if we had a 0 across all of everything here, then that would mean that it is our 4th option, which is a Thursday. Okay. Just in this particular data set, the business is only open 4 days a week. We only have data for 4 days. Okay. So the concatenation component is when, so all of the indices match up here, right? 1 through 244. And we concatenate them horizontally, axis equals 1. So now we have a data frame that is all of our original features. The binaries have been encoded to binary, and then the 4 option day has been turned into one hot encoding. Once we've done that data prep on the entire data frame, we're going to split into train, validate, and test. And at this point, if this was our first time working with the data set, we would do our exploratory data analysis on the train, right? So we split things up into our X's and our Y's. X's are all of the features. Y is the target variable. Again, we do the same thing on the validate data set. Y is the target, Y is the target. So I'll give you all a little peek that what that Y is going to look like is a bunch of yeses or nos. And if we take a look at this, we could take a look at the original train here, see how the original train in order is index 116, 76, 168, 208, 182, which means all we're doing with the Y is taking the target variable out. Same order of things. Is that tracking? Cool. All right.
And just to make sure, when you're using a decision tree, you can only have one target, or is it possible to have multiple targets? Because that sounded like it's going to get really messy, right?
We will be doing one target here. There's ways of producing multiple different target variables, but that's a bit much. We're just walking before we run. And I don't think in the course we're doing any multivariates. Yeah, don't worry about it. We're working on one target variable at a time. Is that okay for you?
Yes, I was just wondering if I should put an S after target, that Y equals target or target.
No, y equals target. Y equals target. We will jump up and down and scream at the top of our lungs if we're doing multiple targets. Nothing to worry about right now. Don't get wrapped around the axle there. We'll just make our Y one column, right? There are ways of doing multiple targets, and that's way outside of scope for right now. the scope for right now is the question, are y'all comfy with the data set that's highlighted right here? Total bill, tip, our target, and then we're splitting up our Y to always have our target. All right. For my next trick, I'm going to build a decision tree classifier. And what this line of code is doing is producing a blank, untrained model. That's all this is. So there are a lot of potential arguments that go into the decision tree classifier. Most of the defaults are pretty good. The one default that's crap is the max depth. If you don't put in the max depth, you will create an overfitting machine 100% of the time, because the max depth will not be limited or bounded. So it's imagine playing 20 questions if you didn't have a limit on the questions. You're gonna get to the answer, but you end up with an overfit model, overfit on the training data. So we're gonna do a max depth of 3, meaning 3 different decision points. I just want to start here, and then we can explore from a little bit further. So running this cell produces a blank model. It's not too fancy, but this model by its nature is accepting all of the other defaults. The max depth is set to 3. So we're not playing 20 questions, we're playing 3 questions with this data set. And by setting the random state here, I'm ensuring that my outcomes are reproducible. Does your random state have to be 1, 2, 3? No. I'd say pick something and stick with it. So we have an untrained model. This is, I've noticed, this is almost anticlimactic. We're going to fit our model. Okay, we just fit our model. Let sklearn do all your calculus, do all your linear algebra for you, because now we have a fit model. Fit on what? It's fit on the X train, and it also knows the Y train. So it knows the input variables, the features, and we're sending in our labels, right? This is our dictionary definition of supervised learning. We have the answers, we have the labels. So you may or you may not take my word for it. We have a classification model now that's trained, and that training happened really, really quickly, right? It's almost anticlimactic. I've noticed a lot of folks in we do these like Saturday workshops. A lot of folks are like, oh yeah, model. They don't want to see me do data visualization, right, or exploratory data analysis. But this is kind of okay. We fit the model. It's kind of anticlimactic, right? But now that we have a fit model, what can we do with it? Well, the first thing that we can do is we can visualize the model, and this is something that's really, really useful with decision trees. There is a tool called GraphViz, and check out this GraphViz. GraphViz is going to take in that CLF, that's short for classifier. CLF is short for classifier. You could literally name this model as a variable. That's totally fine. You could name it tree, because that's exactly what it is a tree. We're sending in the trained model. How do we know that it's trained? Fitting equals training the model. Okay. We take in our feature names. We've got some other arguments that are helpful. And then we produce, check this out, just takes a moment. With GraphViz, we can produce a visual diagram of the decision tree. And as we look at this, our tree was 3 deep, right? Max depth was 3. Now, on this first decision point, determining if a given table is a smoking table or not, the most important feature is if that day is Saturday or not. That's kind of interesting, right? So see how the trues go left, the falses go right, and then we get another decision point. So let's take a look at the days that are Saturdays. So that this Gini coefficient here is a measurement of how much like that ranking, right, of the importance. The number of samples, that's the number of observations. And we see here that the number of true observations, 84 versus 52. So it looks like we have 84 diners dining at the restaurant on Saturday. And so of those 84 Saturday diners, the next decision point is based on the tip. Is the tip less than or equal to $1.98, right? If the tip was lower than $1.98, the next decision point, that third layer deep on this side, asks if the day is Thursday or not. And so looking at this one, this is predicting on a Thursday, on a given Thursday, if somebody's there on a Thursday and they've tipped less than $2, then this value here is picking up that they're smokers. If they are, if the day is not Thursday, then we have a different distribution of values. Okay. So these are the value is the outcome. So our trees can get really complex if they're like 30 deep, right? They can get real complex and they can get very, very, very overfit. And so let's take a look like this, looking at this Thursday thing, it doesn't even, it looks like we have like 1 non-smoker and 15 smokers on that Thursday. Kind of wild.
So no matter your depth of questions that you put in there, that first rule will always be the same.
The first rule is not always the same, right? If this is a different data set without Saturday, we're going to get something different. But look at in looking at these output values, there are 84 observations where this is Saturday, 52 observations where it is something. I'm sorry, the day is Saturday. So this decision point is day sat less than or equal to 0.05. So actually, if the day is Saturday is 0, then we're going to the left here. Because this is the comparison. Every comparison is some sort of less than or equal to thing, even on a binary like 0 or 1, right? But we see here that this is the largest chunk of numbers. See how where the day is, the day sat is 0, there's 84. So going to the left here is any day but Saturday. I know the true is confusing here, but look at the operation and the comparison here. When the day sat is 1, this comparison will be false. Right? But see how the number of the value of how much information this question is giving us is, we can see that in the number of observations. See how this is splitting up this observation into 2 large chunks. Whereas these other decision points further down the tree, we're getting 20 versus 13, right? So that the more important the feature and the measurement, the higher up the tree it is. Does that answer your question, David?
Yeah, it does. Now, and I'm just staring at the Saturday. And so knowing how it's encoded, with those dummy variables,
yep.
Saturday would be looked at as a 1, right? And every other day would be a 0.
Correct.
But
Correct.
It's saying if the left is like yes, right, and the right is no.
The left is yes based on the highlighted comparison. Yeah.
Right. But if they're saying the day is Saturday, wouldn't it be greater than or equal to 0.01 or whatever it would be? Like that way.
Yeah. When your day is actually Saturday here, it is the number 1.
Right.
When you look at number 1 less than 0.5, that's false, right? 1 is not less.
Oh, okay. So if it's less than 0.5, it's going false.
Yeah.
Okay. I was reading that as if day is Saturday less, and then it's going.
No. When you say if it's less than 0.5, it
Right.
is Saturday, meaning the value in the column day sat. So if the value in the column is 0, we go to the left.
Okay. That I was saying if the column was, I was thinking it was like, oh, this is 1, you're going left. I'm like, well, does it make sense if it's, or if it's 0? I don't know. Anyway, I'm gonna confuse myself. I keep talking, but I
The magic is all going to come from the comparison operator at the top. Let's look at something a little different than looking at a comparison operator on a Boolean. Tip less than or equal to $1.98. This is a true or a false. The trues flow to the left, meaning that there were 61 people that tipped at or below $1.98.
Right.
I'm sorry, I'm saying that part backwards. Actually, the 61 is going straight down because 46 plus 25 is 61. I'm not sure. Let's see. Something looks funny here. Yeah, that's all right. Now I'm confusing myself, David.
Sorry.
That'd be 71.
Yep, it looks a little off. It looks a little off. I need to pull out of the detail a little bit here. The big focus here is see how we're focused on a column and saying which observations in that column are less than or equal to or less than some other value.
Right.
It's all a bunch of yes no questions all the way down. That's all it is. Bunch of yes no questions all the way down.
So from the first level, starting back up at day_sat.
Yep.
If we are Thursday, Friday, or Sunday, that's the true one. So if
correct, because zero, that means 0 is less than 0.5. Yeah.
And so looking down, I just want to try and read it correctly. So in this example, we're either Thursday, Friday, or Sunday. And then the next orangey color to the left says that the tip is less than or equal to $1.98. What are the chances of that? That's where I get confused by the Gini sample value.
Ignore the Gini bit, please. Please ignore the Gini bit.
Okay.
It will do us no good at this stage in the adventure.
The samples and the value give us any value?
Yeah, looking at this, let's see, number of samples. That's the number coming in. And the value, I'm thrown off a little bit. I need to check the docs on GraphViz on this value business here. But
it looks like that's adding up to our total sample. So it got split into something.
Right, because we're sending in, let's see.
It should be 71 and 16.
Yeah, I'm not sure what's going on there. I don't know what's going on with the samples. Those should be completely like arithmetically discernible.
Well, it is. I see the 61 plus 26 is equal to the 87. And then we take that and we split it again. Oh, I'm seeing what you, okay, I get what you mean, that it should keep going down from there.
Yeah.
Okay.
Yeah.
So then as I look at this data, how can I interpret that there is a higher likelihood that a person's a smoker if, I guess that's where I started to get confused because I was trying to focus in on the numbers.
Sure. Let's see. If you're looking for a probability, I can give that to you outside of this. But if you look at the proportion of samples broken down by things, you can do the arithmetic and find the proportion, which is the probability, right?
So then I still have to like analyze this. I'm not gonna like look at it and be like, oh, look right there, there's my answer. I still have to analyze it a little bit more.
Yeah.
Okay.
And what visualizing the tree helps us do, here's the big takeaway. Don't spend zero effort on this Gini coefficient, please. The thing that matters is what's the first decision point. This gives us the most bang for our buck. And then under the second decision point, of all the possibilities where the day was not Saturday, which is to the left here, where day sat was 0, we go to the left. The next most valuable decision point is if they tipped less than or equal to $1.98. So
That makes more sense. Thank you.
yeah.
Is there any significance to the blue color on some of those?
Probably, and I don't know off the top, I'm not remembering off the top of my head, and that's a really good question. Let's find out. What is this? Graph viz blue versus red. Hey, let's try and figure this out. Okay, none of that is helpful. That's just a list of colors. I did not do my homework on that before prepping for y'all. My apologies. Let me write that down.
But that was just generated itself. You didn't tell it what colors to use, or?
No, I didn't. I don't know off the top of my head, Barbara. I'm writing that down right now, so I can come back to y'all. Is that okay?
Thank you.
All right, cool. So this tree helps us. So yes, we do need to spend a little bit more time with the graph viz docs, right? But you could take this and put it on a stand. You could pull this into court, and we could say, are any of these features here, total bill, right? Total bill, table size of the table, Thursday, Saturday, are any of these, like, if this is not something like tips and smoking status for restaurant goers, is this like a loan application for a mortgage? Are any of these protected classes, right? And that's right out of the gate. I'm arguing that because we have the ability to visualize our tree, we have the ability to interpret our model, which means we can put it on the stand and answer questions of how is this model impacting people's lives, right? So I think there's a pretty huge ethical component there personally. A lot of models aren't quite this interpretable. I'm pretty partial to decision trees for this reason. Right, so we built a model first by building an empty blank model and specifying the max depth. Always specify your max depth or you're going to have a bad time. You will have an overfitting machine. We fit the model, which is pretty straightforward, and we can render the decision tree. And now what we'll do with our model is we use our model. Remember CLF is short for classifier. And we will use our classifier to check this out, make predictions. So now that we've trained our model, let's have our model make predictions based on the training data, and we can hold a list of predictions. So looking at the predictions from this model on train, we see that the first row, the model is saying, well, we don't have a smoker. Second row, we do have a smoking table. We're predicting a smoking table. The third row, we're predicting a non-smoking table. Now here's a pretty cool one. We have this function on the decision tree model, the trained model, called predict proba. And I think this might hit something that Amanda was asking about on calculating probabilities. So with predict proba, we're going to send in our X variables. And I'm taking a look at just the first handful of observations. And so let's check this out a little bit. Why train, we'll look at only the first three. Why train is the actual values, which is no for these records. But when we look at the predictions say no, yes, no. And when we look at the probabilities underneath those predictions, we see there's like not even a 60-40 on that first no, almost a 40-60 on the second row. And then on this third row, boy, howdy, we're like 82% sure, or at least we aren't, but our tree is almost 82% sure that this third row is not a smoker. So it's very curious. These first two rows look like inverses of each other, or they're not inverses of each other, but it doesn't seem terribly sure, right? So we can, in fact, produce the probability outcomes for each individual observation. What you may be more tuned into and trained to look for at this point is what the accuracy is and what our other classification metrics are. And here's how we do it. On the CLF model, that CLF model that's been trained, we can ask it a score based on the features, and then we send in the labels. So CLF score defaults to accuracy, and we send in features, and then we send in the labels. And this will give us back the accuracy with a nice little format string. We can clean up that format a little bit. Okay, accuracy to the decision tree classifier on the training set is 71%. And remember, accuracy is the total number of true predictions, true positives and true negatives over every prediction. So this is probably better than just guessing. It's probably better than our baseline. Actually, I should have defined the baseline in here. That would have helped tie it into your last lesson. So let's do that. Let's see. Train dot smoker dot counts. Okay, so if we say let's build a baseline. Let's see. So if generally it's a good idea to make our most common class the mode of these values to be our baseline. So we could say baseline is no, and then we can say that our baseline frequently frequent, and then we can say train dot smoker is train dot most frequent dot mean. That's awesome. I love that error message. No, because it's trying to do string concatenation. Let's see. I need to do double equals to compare two columns like that, and then I can get the mean of the column. Okay, cool. So our baseline accuracy is the number of times that we make a correct prediction. So is this model valuable? My argument is, well, our model is 71%. Our baseline is 61%. So I will argue that this model has more value than the baseline. Right? Forgive me for not doing the baseline. So by guessing that everybody smokes, we can say, well, just based on the numbers, if we predict everybody is a non-smoker, we will get that right 62% of the time. But we built a model, and now we're up to 71% of the time. Okay, so we'll print out the accuracy, and if we're so interested, we can print out the classification report as well. Accuracy is listed on the classification report right in the middle. And looking at what we choose as the positive prediction, we can see that when we look at we're trying to make a smoking predictor and make yes the positive prediction. No value judgment here. Just it's kind of like a medical test if you're testing for the presence of a flu or something. Positive if you have it. Precision. So our positive predictive value, well, not great, and our recall is garbage here, right? If we treat yes as the positive case. Okay, so what I've done, and I know I shimmed in the baseline prediction or the baseline accuracy. Here's your decision. If your baseline accuracy is beat by the model, how well the model performs on your training data, then it's probably worth moving forward. There is value in continuing to model if you beat the baseline, right? So now that we've trained our data, we've trained our decision tree on the training data, we've established that it's 0.71, so 70% accurate. Recall and precision are not great, not great at all. Let's see how this model performs on out of sample data, right? So pretty high accuracy on the training data. And but we need to know, how well does this model perform on out of sample data? That's the name of the game, right? If the name of the game was, how does your model perform on in sample data? We wouldn't make out of sample data. But the hokey pokey, what it's all about is how well does your model perform on data that it hasn't seen before, okay? So here's what we're gonna do. You remember CLF.score. Remember where CLF was trained on X train and Y train. But if we want to evaluate this model, to evaluate the model trained on new data, the arguments coming into the .score function, that's .score method rather, are going to be not train, but validate this time. X validate and Y validate. And it's just a little convention here for X's to be capitalized, Y to be lowercase. There's no code reason for that to exist that way. Okay, so 68% accuracy of our trained model on out of sample data. And so looking at 68% compared to 71, this is technically a little bit overfit, right? Depending on the scenario, like, is that the end of the world? Do we need to trash the model and start from scratch? Well, expect that you're gonna have some overfitting in general, but 68 to 71, not that huge of a loss. And if we compare to that baseline, 68% is still beating that baseline guess, right? If we just guess that nobody smokes, that none of the tables smoke, we're accurate 62% of the time. On out of sample data, we're doing 5% better, which, depending on your scenario, that's either a big deal or it's not a big deal, right? Just kind of depends. We can also make, in order to produce the classification report, we need to produce our list of Y predictions. So see how we're using this same variable, CLF. That CLF variable, that classifier, was trained on X train. And now we're going to use the trained model to make predictions off of the validate inputs. And this gives us, so YPred will be a NumPy array. And so it's predicting smoker for the first row, non-smoker, non-smoker. And if we compared that to the actual, which is YValidate, we could look at the first three. Let's see what we have there. Yes, no, no. Okay. So this is just a little peek, but let's take a look at the classification report. Accuracy, 68%, which we already calculated. Those precision and recall scores are really looking like dog meat, right? Those look like dog food. Those aren't fun, right? That recall is pretty nice, but if we treated no as the positive prediction. Okay, so looking at what we've done, I want to recap a little bit. We did our acquisition, preparation, and splitting, encoding of anything needing encoding. So we encoded strings that were only 2 values into binaries. We did get dummies on the day, which had 4 outcomes. We concatenated our get dummies data frame with the rest of the data frame. We split the data frame into train, validate, and test, and we're stratifying by the target variable. so that we don't have an accidental randomly generated cluster of too many or too few target variables in an unbalanced way. Then we set up our X's and our Y's for train and validate and test. And right here, this where we make this CLF variable, we just keep using this variable all throughout. So think of this CLF variable. Once we train it, once we fit this, it's a trained model. And then we use this model when we want it to explain itself with GraphViz. We send it as an argument. When we want to make predictions using that model, we use .predict. If we wanted to get the prediction probability, we use that same model, CLF, right? And we can use CLF to get the score. And we feed in our X and our Y. The first time we're evaluating the accuracy of the model, we need to evaluate how well it performs on the training data set first. And we need to see if that beats the baseline or not. If our first model doesn't beat the baseline, there might not be value in continuing the model, right? All right, cool. I want to show y'all, so that comparing 71% accuracy to 68% accuracy, not a huge amount there, but I want to show you the worst case scenario with a decision tree classifier. Would y'all like to see the worst case scenario? The worst case scenario with a decision tree classifier is this. If you make the classifier object and you leave off the max depth, it will interpret that as go as far as deep as you need to overfit. So let's build this with a max depth that's unset, that's unbounded. And let's see, I gotta clean this up a little bit. Let me clear my output. I'm gonna make the most overfit model that we'll ever see today. So I'm gonna do my imports, define my split, acquire the data, do my prep on the data. Okay, split into my X's and my Y's. Awesome. So again, for the avoidance of doubt, I'm purposefully avoiding the max depth argument here. If you leave that off, the decision tree will go as many layers deep as it needs to. And let's take a look at what that GraphViz output is going to look like here. That's bananas. And it keeps going. It doesn't even fit on one page. So again, the higher up your decision point is, the more valuable it is, the more information it gives us. But what we're looking at here is, I'm not even going to count the number of split points here. It's a whole bunch, right? But check this out. We're going to make some predictions, check the prediction probability. Hey, these are looking a lot better, 100% on the predicted probability. Remember earlier we had like 57 and like 43, right? So let's check this out. Let's build our, I'm gonna delete this one. We're gonna build our baseline. Our baseline accuracy didn't change, right? Just because we made a new model, baseline is 62%-ish. But when we fire this model up, 100%, 100%. Oh my gosh, ring the bell, ding, ding, ding. I made a perfect model, oh my God. Do you believe it yet? It's even perfect on recall and precision. What's your spidey sense telling you on this one? Something's wrong. If you get a model that's 100% accurate, 100% precise, 100% recall, start feeling funny. Have that spider sense should be going off. Your spidey sense should be tingling, because check this out. I'm going to scroll over and we're going to evaluate. Let's see, hey tree that has as much depth as it needed to completely get 100% on the training data. How do you perform on out of sample validate? 66%, right? 66% accuracy. And if we go into the classification report, yeah, our precision and our recall are not fabulous either. So if we're comparing 66% accuracy to 100% accuracy on the train, you know immediately if your training, if your model, when it performs on training data, is 100% accurate, you're in overfit country, right? So some ways of setting your, the first way to make sure that you're making a model, making a decision tree that can play well with out of sample data is this max depth. Earlier, I set it to 3. This model may benefit from having a higher number, right? Because this is only making 3 decision points. Let's see when we make 5 decision points instead of like 20, right? When we check with 5 decision points, okay, we have 5 different decision points. We're getting into a little more nitty-gritty detail here. And, okay. A little less certainty, which is probably a good thing here. Baseline hasn't changed. And now, instead of 100% accuracy, I've changed the depth of the tree to 5 questions. 80% accurate on training data, not bad. 80%, that recall on the yes positive case is just awful. Let's see how this, so we're 80% on train. Let's see how we perform on validate. 69%. So that difference is pretty large, right? 80 to 70 and some change, right? Or 69%. So this is a sign right here that we're overfit. Number one way to avoid being overfit is to not set our max depth so high. So 3 looked pretty useful. Our model was evaluating on train and validate pretty close. If we made this 2 depth instead of 3, we can run this again. See, only 2 decision points that time. And we'll take a look and get the baseline and get the accuracy. Okay, accuracy of the decision tree classifier on training is 69%. Let's see how it performs on out of sample on the validate, 69%. So we don't want very high performance on the training if it goes away when we look at out of sample data. But when I see that my model is performing 69% accuracy on training and 69% accuracy on out of sample data, like validate, that feels like a sweet spot. That feels like a good sweet spot right there. And we can go a little bit further and compare. Boy, howdy, that recall is garbage. Look at that. Yikes, right? So this one's a binary classifier because we're predicting yes or no on if we have a smoking table or not. It is entirely possible to go through the same chain of events on a multi-class classification where we have not a yes or no outcome, but a Setosa, Virginica, or versicolor, like the Irish data set. I have, this is a one-to-one representation of the code that's in the curriculum with the Irish data set. So I'm going to push this up so y'all can play with it. These do not contain any of the exercises though. So something to watch out for is just always remember that max depth is critical. The max depth, I don't have a rule, like a default rule, but I'd say generally make your depth less than the number of features you have, right? Or you're going to have a really gnarly, definitely an overfit model. Cool. If we did the same exact process with the Iris data set, everything is staying the same except we're using the Iris data set, and I'm using that from the Pi data set. So we split our data, train, validate, and test. We set up our X's and our Y's, and then we make a blank decision tree, an empty decision tree model, specifying the max depth. Always specify your max depth. We fit the model, which means we're training it on the training data. And we can visualize it if we want. Now this graph is going to look a little different. So we have 1, 2, 3 decision points because we set the max depth to 3. And this is so wild. It looks like if our max depth is 3, the 3 most important questions we can ask are only depending on one feature, the petal length. Isn't that wild? Like we have petal length, petal width, sepal length, and sepal width, but the first 3 most impactful measurements are all about the petal length, which is kind of interesting, right? And we see that we have 28, 28, and 28. We have an even distribution because we stratified by that target variable, which is the species. And let's see how this model performs. So we visualize it, make some predictions, look at some probabilities. All right. Our accuracy, hey, accuracy is 96%. That's pretty good on in sample, right? Okay, recall and precision, not looking too shabby, but we gotta see how we perform on out of sample data. What's the accuracy on validate? Hey, 94%. So it's a little bit over fit, but I'll take it. I'll take it. I'm comfy with that. And we can make some predictions on the X validate, and we can produce our classification report. And that classification report, it's not squeaky clean. It's not but that's pretty good. So this is literally out of sample data. The Setosa is rocking it. The prediction on Setosa looks to be pretty good, both on precision with power of the positive predictive power, and on recall, which is our true positive rate. So our true positive rate is 100% on Setosis. Our true positive rate when we look at versicolors, treat that as the positive case, 100%, not bad, right? For out of sample, that's pretty good. That's pretty good.
Do we ever use the test data?
Yes.
In this case, sorry. I mean, I'm sure we use it elsewhere, but.
So here's what we're going to do. And this I didn't prepare an aside on this, but I'll put this in the notes. That max depth argument is something called a hyperparameter. It's something that is not coming from the data itself. It's something that we are making a decision on. And so we might make 2, 3, 4, 5 models more potentially with different features, with different hyperparameters. So we might make a handful of models and see how, and what we'll do is find the model that performs best on our validate set. So it's almost like we're cherry picking, right? And the only way we can get away with cherry picking models that do the best on validate is because we still have that test data out of sample, because we still haven't seen the test data set. So our workflow here, would be train a single model and see if it beats the baseline. If so, keep going. If not, maybe baseline is okay, right? And then after that, we'll train a model or evaluate a single model on validate data set to see how well it performs on out of sample data. Okay. We might then make or tweak a few other models with different features. This is where feature engineering may come in, with different features and different hyperparameters. I mean, literally, you can make 2 different models where one is the max depth is 3, the other is the max depth is 4, right? And then we'll evaluate our handful. You know, we might not want to make hundreds or thousands or dozens, but a handful of models. Our handful of models on validate. then pick the best performing one. It feels like cheating because it is, because we're cherry picking what's doing best on out of sample data. Once we've picked our shining model, then we'll evaluate its performance on the trained data set. And once we're touching that trained data set, we really put that off as long as we can, right? That the validate is there kind of as a way of its validate data set is out of sample for what we're training. But once we start making a handful of models that are proving their value, it's almost as if we're using that validate to kind of tweak our more model candidates. And then, all right, we've done a little bit of tweaking. We've got our best performing model on the validate. Now let's evaluate that on the test data set, not the trained data set, but the test data set. Did that answer your question, Amanda? I hope it did.
Oh,
Hey,
sorry.
Ryan.
I put a thumbs up. Yes.
Oh, cool. I didn't. You were out of frame.
My
Sorry.
bad.
I was like cycling through the people trying to see your face.
I'm sorry. I never
okay,
put
it's
the
okay.
mute button quick enough.
Hey, Ryan. So just looking at
Hey, David.
this, so the iris data set, I mean, there's a pretty strong correlation between the features, right, and the target variable, which is why I think that decision tree worked pretty well when it was having to, decide if it was or wasn't, a certain species. There's a reason with that tips data set that just wasn't that strong for the most part is because the features really don't correlate that strongly to whether someone's a smoker or not.
They're not great. Like what we saw is that the model was more effective than just running with the baseline, right?
Right.
But yeah, 69% accuracy. That's not a lot better. I mean,
it's better than a coin flip, right?
Better than a coin flip, and it's better than the baseline because the baseline was better than a coin flip, right?
Right.
Yeah.
I guess that can show us if there's a stronger correlation between features and target. Or I guess maybe this is more outside the lesson, but if we see that, like, hey, we're running a decision tree, we're not really getting that strong of like if we're stuck in the 60s, we're like, you know what, this may not be the best model to go with. Like there's the features just aren't working the way it needs to help the machine like understand.
Yeah, they're either we don't
predict.
have enough observations, like both the iris and the tips data set are not the best examples in the universe because they're dealing in the hundreds, not the thousands or the tens of thousands of observations, right? But the more I look at this tips data set, it's kind of wild, right? There's not, it's been my pet project to turn this particular data set inside out as much as I can. And there are some days in this diner where it's like literally a smoking day and it's a non-smoking day. I think Thursday is like the smoking day. But all of these features aren't great predictors, right? The smoker versus non-smoker, the bill and the tip are pretty close together. There's a lot of a lot of the time, like these might not be good predictors, right? The best predictor might be if you see a pack of smokes in somebody's, shoulder, not how much they're purchasing. So in this particular data set, these other features probably aren't the best predictors. Yeah, I think is that what you're getting at?
Yeah, just you can just you kind of look at the features like, man, these really aren't. They're really not correlating with the target that well. Like they're not that strong of an indicator.
Yeah, if it's beating baseline, thumbs up. But if it's like not beating baseline, then these might not be the right features, right? And we may have to in the scenarios in our report for, hey, what have you been doing lately? We may have to come to the table and say, you know what, these aren't great predictors, and the best I can get my model is just under 70% accuracy.
Like I'm not going to stake my life on this model predicting whether someone's a smoker or not.
I wouldn't stake my life on it, but I'd stake other people's money on it. Right? If we can go from a baseline of 60% to an accurate prediction on out of sample at almost 70%, it's up to the business owner and the stakeholders if that's a big deal or not. Right?
Yeah, what they're comfortable with.
Yeah, because I don't know what that means. Does that mean in this case there's not a lot of revenue difference, but maybe this business owner for this restaurant is considering making it a non-smoking restaurant voluntarily, and it, you know.
So in industry, like how is that? Who's determining what is an appropriate number for that? Is that the team lead of the data science team, or is that the VP who's asking for the information, who kind of says, you know, I want to see at least this kind of rate?
It's a hell of a question. The short answer is yes, all of the above. Right.
There's a lot of context contingent on a question like that. Like it
Sure.
would certainly depend on like the needs of your product owner versus your client versus how much leverage that you have as a data professional in your role on a developer team, things like that. Like there's a lot of factors there to take into account.
Cool. Yeah, just curious, like how that threshold is established of what is okay and what isn't.
If you're doing like a Kaggle competition, right? You know, for like some sort of cash prize or something, that's one thing. But there might be information that's like industry specific, right? And there may be a scenario with our baseline where our baseline is not actually something as simple as the most frequently occurring observation. That's a pretty blunt tool. But what if the baseline we're trying to beat is the last model that somebody built, the last person before you were on the team built? Right. That's also a scenario. So like that term baseline doesn't have to always be the mode, but it could be the number to beat is really how I look at a baseline. It's the best we've got so far. So that baseline could be what the last consulting company came in and built. And if we can beat the baseline by a percentage point or two, like if we're talking like sales revenues and lots of figures, that could be a real big deal, right? Or if we're talking like telco churn or something like that, you know, depending on the cost of acquisition per customer, if we can make better decisions on if they're not going to churn, save the company potentially a lot. So if you can attach the dollars and cents to the predictions, you're not always going to have that luxury, but if you can, all the better.
Great. Yeah, just kind of I know it's going way beyond. I was just
that's
a
perfect question to be asking right now. Is how do you know you're done, and how good is good enough is what I'm hearing there, and how do you know, like in this smoking data set, yeah, we beat the baseline, and I wouldn't be surprised if we did not just a decision tree, but some other classification algorithms and played with things. We might be able to do better than we're doing with this one right here. But looking at, okay, we can do a 10% accuracy increase on the baseline. What does that mean to the business is going to be different for every business in every scenario. It could mean nothing, or it could mean like your VP hits their, you know, she hits her bonus figure for the year or whatever, right? or the product lead is like, okay, we can ship this product now versus close the doors on the product, depending on.
Right.
So it just depends.
It's like our KPIs are dependent on this. You better get it right.
Yeah. And 69% accuracy on train. I'm not terribly impressed by that because it's on the training data set, but 69% accuracy on out of sample validate. That's not terrible. That's not terrible. So what I'm going to do is I'm going to restart these kernels so everything runs in order. And then I'm going to add, commit, and push this business for y'all. So I've got two demo notebooks. One is the Iris decision tree. This is completely mirroring the curriculum. The tips data set is mirroring everything in the curriculum except adding it. I've added the baseline, and I'm using a data set that's not listed on this specific module. So those PDFs, for some reason, my GraphViz is creating duplicate variables or duplicate outputs. I still need to troubleshoot that a little bit, but I am not going to commit those as part of this. Add final Iris and tips demos. Push my work.